In this video, we will be talking about surface integrals. And just a little heads up, if you hear any lightning or rain or anything like that, yeah, there's just a really, really crazy storm going on outside. But, that's besides the point. Math is more important than anything else. So let's get right into this video. So we're going to be talking about surface integrals, and more specifically, we're going to be covering surface integrals for scalar functions in this video. So I'm going to be running through some practice problems, but I'll also show you the general formulas of what they are. So let's write down surface integrals. And just a quick note, a surface integral is just a step up. So it's just a step up of a dimension compared to line integrals. So let's go ahead and start. Well, the first formula that you need to know is just a super general formula. You have some region, and this is going to be defined by your surface S, and you have some function of x of y of z with your differential of a surface. But this is not the helpful formula. This is just a super general formula. This is not the actually helpful one. The actually helpful formula is a double integral of your region. Okay? And this region is parameterized by some I don't even know what this is called. Some vector valued function, whatever. It's parameterized by uv. So the parameterization of two variables now, before it was t in line integrals, now you're parameterizing with u and v. And you multiply this by some magnitude of some partial derivatives and their cross products. So t just stands for, let's just write this down in a more consistent notation, r of u, so this is the u partial, crossed with the v partial of r, d of a smaller, d of an area now, actually. So this is your surface integral, actually. So these are the forms that you'll actually be using, but this is the more useful one. And I'm going to show you just another special example of this with conditions. Let's write down with conditions. So this formula for surface integral has conditions. This is the one that you're mainly going to be using in most of your problems. So you're going to have some double integral. Again, you're going to have some region. But for this one, you're going to have your parameterized function as so. X, y, and z. But z is actually going to be some function. Let's pick the next letter. Some function of x and y. So you don't need to parameterize x and y. X and y stay the same, but z is just your function of x and y. And this is only when z has some explicit function to it in your surface integral. Times the square root of your function f of x squared plus f of x y plus 1. And these forms just look like a whole bunch of mumbo jumbo right now, but with conditions. Let's write it down. With conditions. But as you get into the problems, you'll start to understand what all this means. Now, a neat trick that you can do with surface integrals is find the surface area of some function. Or you can find an area. It doesn't matter. You can find some surface area of a function by setting your f of y of z equal to the function just of 1. So this guy right here, it would just be equal to 1. Or this guy, there is no parameterization for just the constant 1. So we want to find the surface area of this plane in this region 0, 1. So just a real quick example of what you're solving for. This is your plane. So in the problem we had 2x plus 3y plus z is equal to 6. So this is your plane. This is your function that you're trying to solve the surface area of over this region 0, 1, and 0, 1 for x and y's. But let's turn this off right now. Let's actually show you the region. Let's show you the region that you're actually solving your integral for. So as you can tell, this red part here is just some part that you took out of the blue region, but it has specific conditions. if you were to just create this, move this vertical with the xy plane, it's actually just a square over your bounds of 0, 1, and 0, 1. So we're trying to find the area of this shape here that is part of this plane over just the region 0, 1 of x and 0, 1 of y. And we can actually solve for that using an analytical method, or just a mathematical, let's not use fancy words, just an analytical method using surface integrals. Using an analytical method to solve for this, we can actually find the surface area, as I showed you in the Desmos, of this plane over this region, 0, 1, and 0, 1 for x and y. But what formula will we be using here? Well, we can use both of these two. Both of these two work because they're technically just equivalent values of each other. This one is just a derivation or just some algebraic manipulation of this magnitude cross product here. But this formula is easier because you don't have to solve for no cross products or anything like that. You just need to solve for partial partial derivatives. There you go. But we don't meet this condition, z is equal to f of x, y. Well, we actually do, because we can manipulate, or we can algebraically manipulate this function to set it so that z is equal to, 6 minus 2x minus 3y is equal to z. Now we've satisfied this condition. Z is equal to some function of x and y. So we can actually solve for our partial derivative of f of x here. So the partial derivative of f of x is just negative 2. And our partial derivative of y is just negative 3. Therefore, this square root is just equal to, so this is negative 2 squared plus negative 3 squared plus 1. And this is all equal to the square root of 9 plus 4 plus 1, which is equal to the square root of 14. And since we're trying to solve for the surface area, well, our function here is just 1. So our double integral is just the integral of 0 to 1 of our function 1. So this is equal to your function of f of x, y, z here, times square root of 14, because the square root of 14 is equal to this component right here of dA, which is dx dy. But as you can tell, well, this integral's bounds are just 0, 1, and 0, 1. So the square root of some constant, square root of 14 of dx to dy, just stays the same. Square root of 14 still equals the square root of 14. Now, that's the easy way to solve it. Let's show you the more general way, and you can skip this part if you want. This is unnecessary. But you can solve for it using this method here, where you actually parameterize. So we can parameterize this like so. So r of x, y is equal to, well, x just stays the same, and y just stays the same due to this condition. And z is equal to, so your z component of your parameterization is equal to 6 minus 2x minus 3y, because z is equal to this right here. We can find the x partial of this. So the x partial of this is just equal to 1, 0, and negative 2. And we can find our y partial. It's just 0, 1, and negative 3. Now, if you want to find the cross product of both of these, so you want to find the cross product of r of x and r of y. U and v are just variables. They're interchangeable with x and y. And if you find the cross product of this, you get, hopefully you know to solve cross product by now, but this cross product is 2, 3, and 1. And actually, if you noticed, this is just another way of saying a normal vector. And your normal vector is already defined on this plane by the coefficients of 2, 3, and 1 for all your values here. 2, 3, 1. 2, 3, 1 is your normal vector, and 2, 3, 1 is your normal vector when you find some cross product. So there's a little shortcut that you can take, but I'm just showing you the math so that you actually get it for other problems that aren't that don't have shortcuts like this. We want to find the magnitude of this, so we want to find the magnitude of rx cross ry. Let's keep the vector symbols at the top. So that's just equal to the square root of 2 squared plus 3 squared plus 1. And that's just equal to the square root of 14. And if you solve for your double integral, again, of 0, 1, 0, 1 of the square root of 14 dx dy, you just get square root of 14 again. So both your answers were square root of 14. Both of these ways work. This right here is actually just the derivation of this, but I just wanted to show you that they both can do the same things. For this problem, there's going to be a little bit of the little earlier concepts that you learned in Calculus 3. So when you first learned about planes and formulas for planes and normal vectors, this is where all of that comes in handy. And I will do a quick review of that. But firstly, I just want to show you that you have this sort of plane bounded by these points with a counterclockwise orientation. So that won't matter as much other than when you're calculating your normal vector, but I will show you how to do that as well. So we have some plane. Let's see. Why did it do that? We have some plane, and let's go ahead and draw your x, y, and z plane. Bounded by the points. 0. Let's use green. So this is your x. This is your y, and this is z. 0. Okay, 1, 0, 0. This point is 1, 0, 0. This point is 0, 1, 0, and this point is 0, 0, 2. If you want to draw the triangle between this, or if you connect all the dots, bro, I cannot draw a straight line. Holy shit. Hold on, let me use the straight line tool. Okay, that's a lot better. If you were to draw straight lines between each things, then you would have some triangle here. You can shade this in. And this triangle, well, this triangle is just a plane over a region. And what's this region? This is the region on the xy plane right here, shaded by blue. So if we were to actually draw this out on the xy plane, let's go ahead and draw this out again. This region here is just represented by, so this is the xy plane. XY. If I were to draw this blue part out, we would have, let's use blue. If we would have some point on 0, 1 and 1, 0, and let's draw the line between them. Kind of a straight line. Good enough. So this blue region is just this guy right here. These two are the same. I just drew it on the xy plane. And technically, this triangle is just the formula for a plane. So how can we find the formula for this plane over, just limited over this region? Well, we can find the formula using, again, what I said, the earlier vector methods that you used. So we can name this point. Let's name this A, B, and C. And if we were to mark this point would be C. This point would be A, and this point would be B. But we can find the formula for this plane once we find some normal vector. That's going to be important. The normal vector tells you the formula for a plane. So how do you do that? Well, we can find the vector between C and A. Find the vector between C and A, and find the vector between C and B. And let's write that down. The vector between C and A is, well, this is 1, 0 for the second component, and -2 for the third component. The vector between C and B is just 0, 1, and -2. And if we find the cross product between C and A and C and B, point C and B, you get the normal vector. And this cross product just turns out to be, what is this, 2, so 2, 2, 1. And since this is a normal vector for this, well, what we're trying to find is a normal vector here. RU cross RV is just the normal vector, and we did that already here, actually. So, wait, what I just used, what did I do? So, we can actually find the magnitude of this vector. It's the magnitude of CA cross CB. And it's just going to be equal to 2 squared plus 2 squared plus 1 squared. This is equal to square root of 9, which is perfect square, so it's equal to 3. So this component here is just equal to 3 of your surface integral. Or this part right here as well, is what we did, was these two look identical actually. Right? 2 plus 2 plus 1, 2 plus 2 plus 1. Actually, they're technically not too much. Oh, they are too similar. They are kind of similar. So we have this part of our surface integral already by just finding the magnitude of your normal vector. Remember, this is just a normal vector for your surface integral. So what do we do next? Well, we have to parameterize this. So we need to parameterize this with some function of x and y, or u and v. We can use u and v, but I'm going to use xy because this meets the special condition here. We have our normal vector now, 2, 2, 1, so we can actually write down the function of this green plane. So the function of this green plane is 2x plus 2y plus z is equal to, just pick any point and then multiply and then dot product any of the points with your normal vector. So I get 2 here. So this is the formula for this plane using our normal vector and some point. And if you don't know, and I actually have a video on finding the formulas for a plane. So if you're stuck on this part, then that video might be helpful for you. And we can actually manipulate this function to set z equal to itself. Not z equal to itself, z equal to some function. So this explicitly defines this function. Therefore, we can use this format of the surface integral here. So xy, 2 minus 2x minus 2y. Now that we have this parameterization, we can plug in this into z. So we can substitute all our parameterized values into our double integral. And our parameterized values are just consist of 2 minus 2x minus 2y dA of some region. Now we have to find the region. Well, the region we already drew was the region on the xy plane. So this region on the xy plane that we're trying to solve for is just this in blue. So what are the formulas here? Well, the formula for this straight line down is just 1 minus x. And it's bounded below by y is equal to 0. So your bounds for y, let's write this, 2 minus 2x minus 2y dy dx. So your bounds for y is 0 minus 0 and 1 minus x. And your bounds for x are just 0 and 1. So this is just 0 and this is just 1. This right here is 0.0 and this one's 0.1 and this is 0.0 for your x values. So your x value is just bounded by 0 and 1. I'm not going to evaluate this entire integral, but in the end you just get the answer 1. So by now, well, hopefully by now you can solve for double integrals, but this right here, this answer is 1, and you can go ahead and try out this double integral yourself. And I wrote counterclockwise. This is just a side note, but I wrote counterclockwise because when something is counterclockwise, when the orientation of your surface integral is counterclockwise, the normal vector must point up in most scenarios. So your normal vector right here is pointing up, 2, 2, 1, so this makes sense. Now, if you got the normal vector of -2, -2, and -1, this is still a normal vector, but it's not pointing up, so this is not in line with your counterclockwise orientation. Now, if this said just clockwise orientation, then if this says clockwise orientation, then the normal vector pointing down would make more sense, -2, -2, and -1. Now, for this problem, you're given, again, an explicitly defined function, which means that you can use this form right here. It's a lot easier, but you don't have to find any cross products or magnitudes. You can just follow this format here. So this explicitly defined function already is isolated z, so this is good so far. Bingo. But we're finding the surface area. Surface area. What does that mean? Well, that just means your function f of x of y of z is equal to 1. Another good thing, well, it's a little too perfect for an exam problem, but this is just a practice problem for now. But that means this is just equal to 1. This part of your surface integral is equal to 1. So we have a good bit of piece of information here. Now, how about this? Well, technically this is not f of x of y. This is just your parameterization. So this is technically wrong. But we have your r of x, no, actually r of t, so your parameterization of this is actually, no. This is right, this is right, this is right. Your function f of x, so let's find the f of x of this function right here. The x partial of this is equal to negative 2x, and your y partial is equal to negative 2x as well. We have to find the square root of these values squared. So square this. You get negative 2x squared plus negative 2x squared plus 1. And if you find the square root of all this, if you simplify all this further, you get, you get 4x squared plus 4x squared plus 1. So this guy right here is this part. So we have 1 for this, and we also have this part right here marked off here. Let's write down our integral now. So our integral will look something like this. You'll have some region. The square root of 4x squared plus 4x squared plus 1 dA. Now here's the thing about this. This integral is going to be very difficult to solve. So what can we actually do? Well, we can't actually find our region right now. It's actually impossible because your region is a circle. So we need to switch the polar coordinates here. Sorry, I just burped. Polar coordinates, our best friend. Going back to that. So how do you find your region? Well, your region is just on your xy plane. So let's read our function here. Our function is 4 minus x squared minus y squared. So your region is just any your region on the xy plane. So how do we represent this? Well, on the xy plane, z is equal to 0, so we can just set z equal to 0. And then when we put all the variables of x and y onto one side, we actually get x squared plus y squared is equal to 4. Now, doesn't that look familiar? This is just a circle with radius 2. So let's try that. This is just a circle with radius 2. This is an oval. This is a circle. There you go. So this is just a circle with radius 2. Now, this circle with radius 2 has very easy bounds to find. Your bounds for this are just 0, 2 for the radius, and 0 and 2 pi for the theta value. That's pretty easy. Now we need to turn this into polar coordinates. Okay, so this is actually going to be the most annoying part. We can factor out 4 out of x squared plus y squared plus 1. And x squared plus y squared in polar coordinates is just equal to r squared. So we have 4r squared plus 1. Therefore, our integrand is 4r squared plus 1. And dA in polar coordinates, so dA in polar coordinates is equal to r dr d theta. So let's do r dr d theta here. And now we have an integral that's possible to solve. So using u substitution, so we set u equal to 4r squared plus 1. And du is equal to 8r dr. That means dr is equal to du over 8r. Right? So we rewrite this integral. We get 0 to 2 for our bounds and 0 to 2 pi for our bounds for theta. 4r squared plus 1 is replaced with u because it's equal to u in our new u substitution method. And dr is equal to, so dr right here is equal to du over 8r. This is d theta still. Here's the thing about these r values. They actually cancel out. So what you get is an integral between 0 to 2. Let's just actually just omit the theta integral for now. But you have square root of u du, and our bounds right now are not actually 0 or 2. This is technically not very rigorous of me to say, so I'll just leave that empty for now since we did u sub. So this is du, this is du times 1 over 8, and the 1 over 8 can be factored out of the integral. So we have 1 over 8 outside of here. If we were to solve for this integral, we'd get, what is this? We'd get 1/8 times 2 over 3 u 3 over 2. And that just equals 1 over 4, 1/12 u 3 over 2. So let's erase this part. Make this a little bit more compressed because we might run out of space. And u right now, we need to u sub back everything. So we have 1/12. So u is equal to 4r squared plus 1. So we just replace it with 4r squared plus 1. 3 over 2. Therefore, our integral is from 0 to 2 as our original bounds given. If we plug in 0 and 2, we get, running out of real estate here. Let's move this to the side. But if we plug in 0 and 2 here, we get 17 3 over 2 over 12 minus 1 over 12. 1 over 12. And that's free up some space for us. So we can write more. Let's move everything up. Let's move this up. And the answer so far up. Let's move this up right here. So this is our new integrand. We can actually simplify this further into 17 3 over 2 minus 1 over 12. So this is our new integrand. And your integral is just from 0 to 2 pi for theta. Now we integrate with respect to theta. Do not forget about that. So 17 minus 1 over 12 d theta. Well, there's no constants. There's no variables of theta inside this function. So we just multiply this by 2 pi. And if you multiply this by 2 pi, you get 17 3 over 2 minus 1 over 6 pi. And this is our final answer for this surface integral. Right over here. Let's square it. Let's draw the square around it. Let it be known that this is the answer. So, if you have any questions, put it down in the comments section. And I hope everyone got this very confusing topic. When I was learning this, I was confused too. But a couple of rewatches of this or some other videos with better animation would help you. So, good luck on this topic of surface integrals.